So welcome to my YouTube channel Maths Avatarm. So today we are going to discuss second lecture on uniform convergence of function. So in last lecture we have discussed what is uniform convergence, pointwise convergence, all those things. So today we are going to prove one important result, and we will apply that result to prove directly that which functions are not uniform convergent to some function. It is very helpful. Okay. So let's start today's result. That is very important result. So result is that theorem. Let Fn is a sequence of functions defined on an interval I to R be a sequence of continuous function. If each function in a sequence is continuous, it means each Fn is continuous. And if Fn converging to F uniformly, then F is also continuous. It means uniform limit of continuous functions is also continuous. If each Fn is continuous, then and Fn converging to F uniformly, then F is also be continuous. So let's see its proof. Okay. So let epsilon greater than 0. Okay. Since Fn converging to F uniformly, there will be some capital N belongs to N such that Fn x minus Fx less than epsilon by 3 for all n greater than equal to n and for all x belongs to I. Okay. This implies if I can take my small n is equal to capital N, because this statement is true for all n greater than equal to n. So I can choose my n is equal to capital N. So still it will be true. So it will be true. Okay. So this is for all x belongs to I. Let's say it equation number 1. Now this is true for all x belongs to I. So it will be true for, I am taking a particular point because I want to show that F is continuous. So I will show that I will take a fixed x naught and I will show that F is continuous on that x naught. Okay. So I have taken x naught. Since equation number 1 holds for all x belongs to I, so it will be also hold for x naught belongs to I. Okay. So I am taking x naught. So I am applying x is equal to x naught in equation number 1. So I go equation number 2. Okay. Now we know that sequence is each function in a sequence continuous. So Fn is also continuous. So how we will write in terms of epsilon and delta? Fn is continuous at x naught. Okay. So we have there exists a delta greater than 0 such that F capital Nx minus F capital N x naught less than epsilon by 3 for all x belongs to I such that x minus x naught less than delta. So let's say it's equation number 3. Okay. Now I am starting with this fx minus fx naught because I want to show f is continuous. So I have taken fx minus fx naught. So I will subtract fx and fn x and fn, I will add fn x and I will subtract fn x naught plus and I will add fn x naught, and there the thing will remain as it is. So after solving it, we will get this one fx minus fx naught absolute value. Okay. So what we got? So now we can use triangle inequality here. Fx minus fn x plus fn x minus fn x naught plus fn x naught minus fx naught. Now, what about this inequality? This fx minus fn x, that is less than by equation number 1. What was equation number? Equation number, you see this one. see this equation number 1. What you got? You got this is less than epsilon by 3. So I am taking that is epsilon by 3. Okay. So I am taking next for x belongs to I such that x minus x naught less than delta we have, because x belongs to I can use equation number 1 in that. In equation number 1 this is less than epsilon by 3. And what about this? By equation number 3 it is also less than 3, because what is equation number 3? Equation number 3 holds if x belongs to I such that this happens. So we have this one. So equation number 3 will be very can use it. Now what about this? Fn x naught minus fx naught. This is coming from equation number 1 as well. Sorry, equation number 2. It is coming from equation number 2. So use equation number 2 here. So this implies fx minus fx naught less than, so what is this? Epsilon. Epsilon. For all x belongs to I such that x minus x naught less than delta. So we have taken epsilon and we have fixed x naught and we got corresponding delta greater than 0. This holds. What does it mean? It means f is continuous at x naught. Since x naught is arbitrary point of of I, we get that f is continuous on I. Okay. So it means, so we have proved this result. So we have proved the result that if each Fn is continuous and Fn converging to F uniformly, then F has to be continuous. Okay. So in other words, conclusion of this theorem, so it means we can use this theorem in another way. How? Suppose Fn is a sequence each Fn is continuous on I if Fn converging to F pointwise and F is not continuous, then what can you say? Whether Fn can converge to F uniformly? From theorem what we know? If Fn converging to F uniformly, F has to be continuous. So in this we have taken here F is not continuous. So each Fn is continuous, Fn converging to F pointwise and F is not continuous. From theorem what can you say? Fn cannot, this convergence cannot be uniformly. by theorem we can conclude that this convergence cannot be uniformly, because if sequence converging to f uniformly and it is given that f is continuous, each fn is continuous, then f has to be continuous. But in the conclusion it is given that we have a statement that each fn is continuous, fn converging to f point y, and f is not continuous. What does it mean? Then what can we say? F is this convergent is not uniformly. So fn does not converge to f uniformly. Okay. So we are going to apply this theorem for conclusion. Suppose now question number 1. So that fn x to the power n on 0 1 fn does not converge uniformly to some function. Okay, some function. Because we know that if we take fn 0, so it will be 0. This will converge to 0. And if we take 1, it will converge to 1. And what about if we are taking x in between? So this will also go to 0. Okay. So what is pointwise limit? Pointwise is limit 1 if x is equal to 1 and 0 if x belongs to open. So it means fn converge to f pointwise. Okay. Now what can you say? Because x is not continuous at 1. F is not continuous at x is equal to 1. We get that f is not continuous on I, because if f is continuous on I, it has to be continuous at each point. If you can find a particular point at which it is not continuous, it will not continue throughout interval. Sorry, we will not say that it is continuous on I. Okay, because we have a point on which it is not continuous. So it means fn does not converge to f uniformly, even though it is pointwise convergent to f. Okay. But it does not converge to uniformly to f. Okay. Because each fn is continuous. If because fn x is equal to x to the power n. So x to the power n function, you take any particular n, each fn is continuous function. But its pointwise limit is discontinuous function. So if fn converges to f uniformly, f has to be continuous. But f is not continuous, so it cannot be uniform convergence. Even it is a pointwise convergence. Okay. Now you see question number 2. Question number 2. So I am taking is fn x 1 minus f mod x to the power n 1 plus mod x to the power n uniformly convergent on R. So let's see it. First you calculate this pointwise limit. What is that? What is pointwise limit? So I have R. First of all, I am taking x is equal to plus minus 1. What will be limit at this point? 1 minus plus minus 1 to the power n. So mode of plus minus 1 is 1. So it will be 1 plus 1. So it is 0. So Fn plus minus 1 converts to 0. Now if value of x is in this range, it means mode of x is less than 1. Then what about this? Then what we will get? The x to the power and this will tends to 0 as n tending to where it will go? It will go to 1 minus 0 upon 1 plus 0. It means it will go to 1 by 2. Sorry, it will go to 1. It will go to 1. And what about if x is greater than 1 or x is less than minus 1? It means x mod is greater than 1. Then what we will have? In this case, 1 upon x mod will be less than 1. So what is this? So I can write 1 upon, you take absolute x to the power n common from numerator and denominator, what you will get? So I can write it. So this part goes to 0 because 1 upon mod x is less than 1. So its value will go to 0. Okay. So it means this tends to 0 minus 1, 0 plus 1. It is minus 1 upon 1. That is minus 1. So Fn x tends to minus 1. So what we have? What is my f function? F function, it is 0 if x is plus minus 1. Okay. It is 1 if x belongs to mod of x is less than 1. And it is minus 1 if mod x greater than 1. Now you see that each Fn is continuous function. What you can say about this? This is discontinuous function. Discontinuous on, it is discontinuous at plus minus 1. Plus minus 1. So it means this implies f is discontinuous on R. And what about each Fn? Each Fn is, we know that Fn mod x is a continuous function. So mod x to the power is also continuous. If denominator is non-zero, it is also continuous. So numerator is continuous. So this function each fn is continuous on R. So we know that each fn is continuous on R, its pointwise limit discontinuous on R. Okay, and we have fn converging to f uniform, pointwise, where each fn is continuous and f is discontinuous. What can you say that fn does not converge to f uniformly? By conclusion. Okay. So now see example number 3. We have done it. Is fn x is equal to 1 upon nx on 0, 0, 1 uniformly convergent? We have already checked it. It is not uniformly convergent. Okay. Uniformly convergent in previous lecture. Okay. Maybe in a smaller domain. If it is not uniformly convergent in a smaller domain, it cannot be uniformly convergent in a bigger domain. So we have done that this function is not uniformly convergent. Okay. So now we will show it by the theorem. How? Each fn, you see that each fn 1 upon nx plus 1, it is a continuous function or continuous. Each fn is continuous on closed interval 0, 1. So what is its pointwise limit? Let's calculate. Pointwise limit is, if I am taking x is equal to 0, what you will get? 1 upon n into 0 plus 1. That is 1 upon 0 plus 1. That is 1. Now, if I am taking x in this range, then nx will tends to infinity as n tending to infinity. Now, what about this? Because this will tends to 1 upon infinity, that is 0. So what is pointwise limit of fn? Pointwise limit is, it is 1 if x is 0 and 0 if x is, so we see that f is not continuous at x is equal to 0. Each fn is continuous, but its pointwise limit function is not continuous, and fn converges to f pointwise. And this function, each function is continuous, but this function is not continuous. Okay, not continuous. So what does it mean? Each fn is continuous, f is not continuous, and fn converges to f uniformly. So what does it mean? It means fn does not converge to f uniformly. Okay. So we have done 3 examples. Okay. So what we have learned from today's lecture? We have learned from today's lecture that if we have a sequence of functions and in this sequence each function is continuous and fn converges to f pointwise, but f is not continuous, then f cannot be, then f is not continuous, then f can, suppose we have a sequence of function fn and each fn is continuous and fn converges to f uniformly, then f is also continuous. Okay. In other words, suppose we can use this theorem in another way. Suppose we have a sequence of continuous function and fn converges to f uniformly and f is not continuous, then F cannot converge to F uniformly. Okay. So thank you very much for today's lecture. Okay. Kindly subscribe my channel, like, share, and comment on my YouTube channel. Thank you very much for today's lecture. We will see you in next lecture. Okay. So thank you very much.